Welcome, my dear students. Today, in continuation with the lesson which you have already done, I would like to take up other things in refraction of light. I have talked enough of dispersion of light. I have already talked of recombination of colors also. And I have already talked why exactly a diamond sparkles. All these things I have just discussed. Today I would like to start my lesson with a question. What is that question? Dispersion of light takes place in a prism, but it does not take place in the case of a glass slab Y. Suppose you pass white light through a glass slab, no dispersion of light takes place. What is the reason for this one? Okay, well, just to take up. Now, a glass slab may be considered to be made up of two identical prisms with one of the prisms kept inverted. Once again, it may be considered as a combination of two prisms with one of the prisms kept inverted, as I show in the figure here. I hope you are able to see this one. The first figure. Now, here is a glass slab. It is made up of two identical prisms. You see that? Kanata. And they are cemented together in such a way that one of the prisms is kept inverted. What happens? Though the first prism produces dispersion of light, the second prism folds back all the colors on themselves, as a result of which original composite light emerges out of the second prism in a path parallel to that of the incident beam. That is how no dispersion of light takes place. Here recombination of light takes place, or recombination of colors takes place. Again, I repeat, a rectangular glass slab may be considered to be made up of two identical prisms with one of the prisms kept inverted. When white light passes through that one, though the first prism produces dispersion of light, the second prism folds back all the colors on themselves, as a result of which original composite light emerges out of the second prism. That is how no dispersion of light takes place in the case of which one? In the case of a glass slab. It's a very important question which you should just answer. Next one, I would like to just to take up now lenses. It's a very important thing there. Refraction of light through a glass slab you have just seen. Refraction of light through a prism you have just seen. Now I am just coming to refraction of light through a lens. Before studying refraction of light through a prism, or of course through a lens, let us just try to understand what a lens is. What is a lens? Is it only a piece of glass? No, sir. What is a lens? What is actually a lens? Any transparent substance bounded by two curved surfaces. Again, I say that. You see that one? Alle kanta ideyalla. Any transparent substance bounded by two curved surfaces, at least one capable of refracting light, is called a lens. Again, I repeat, what is a lens? Any transparent substance bounded by two curved surfaces, at least one bracket ಹಾಕ್ತೀನಿ, capable of refracting light is called a lens. Now you will be able to see how exactly a lens is formed here. You see that in the very first instance, second figure and the third figure. You please see that. In the second figure, you find that two intersecting circles. The area here bounded, ನಾನು shade ಮಾಡಿದ್ದೀನಿ, that is one lens. Again you find that once again they are non-intersecting circles. The second one is two non-intersecting circles. Once again you find that I have shaded that portion, that is another kind of lens. That means there are two kinds of lenses. There are two kinds of lenses. One is called a convex lens and another is called a concave lens. The first one is a convex lens, the second one is the concave lens. How do you distinguish between a convex lens and a concave lens? I just give two lenses into your hand, and by mere touching you must be in a position to distinguish between a convex lens and a concave lens. In the case of a concave lens or in the case of a convex lens, it is thicker at the middle and thinner at the edges. In the case of a concave lens, it is thinner at the middle and thicker at the edges. Once again, I repeat. In the case of a convex lens, it is thicker at the middle and thinner at the edges. In the case of a concave lens, it is thicker at the middle and thinner at the edges, as you see here. The first one is a convex lens, the second one is a concave lens. So, the lens that is formed by the intersecting circles ಇದೆಯಲ್ಲ, convex lens, non-intersecting circles form ಆಗಿದೆಯಲ್ಲ, that is a concave lens. And while defining a lens, I told you this one. Any transparent substance bounded by two curved surfaces within brackets at least one. I put that condition at least one. It means you see that here you find once again another two kinds of lenses. A lens is formed by once again the curved surface and a plane surface. It is the first one is called a Plano convex lens because it has got a convex surface and a plane surface. It is a combination of that one. It is called a Plano convex lens. The second one, you find that the second one you find that Plano concave lens. Plano, one side is plane and the other is concave surface. Therefore, it is called Plano concave lens. The other one is Plano convex lens. So, we don't have these two lenses, of course, these two lenses, Plano convex and Plano concave illa, but I have just got the lens that is formed by two curved surfaces and therefore it is referred to as what you call double convex lens and it's called double concave lens. It is also called double convex lens, double concave lens. I say convex lens. By convex lens I mean a double convex lens. The concave lens means I say that it is always a biconcave lens. I hope you understood this one. So that is there. And when I just take up, what shall I say? What is the action of a lens? That is, how is a lens able to refract light? That's a question there. Now here I got two lenses written separately. One is, the top one is a convex lens, the other is a concave lens. You find that. The rays traveling parallel to, or the rays, which one, the parallel rays, when they undergo refraction through the first lens, they will be converged towards a point. You are able to see that. They will be focused at a point. They will be converged towards a point. That is how it is called a condensing lens. A convex lens is also called a condensing lens because it is capable of converging all the rays. It is able to condense all the rays to a point and therefore it is called what we call convergent lens. And the second one, you see that in the case of a concave lens, the rays actually go diverge. You will be able to see that the rays will be diverged away from the lens and therefore it is called divergent lens. So convex lens is also called convergent lens and concave lens is also called divergent lens, because which one? Convergent lens always produces which one actually? It all the rays coming out of that one will be actually focused to the point. Here it will be moving away from a point. You'll be able to see that one very clearly in the figure. Okay, sir. Now I would like to just to take up what the images. I have already talked about the formation of images in a mirror. I have already told you. Before I just talk something about this one, we have got fundamental definitions. Fundamental definitions with respect to a lens. Just like the fundamental definitions which we have discussed in the case of a mirror. The first one is actually center of curvature. The second one is the radius of curvature. Number 3 is actually a pole of the mirror there. And next one is the principal axis and then the principal focus. They are the various definitions which I have just discussed in the case of which one? A mirror, that is a spherical mirror. But in the case of a convex lens, I would like to say that one, you have to just discuss so many things here. The first one is what you call, which one? What is that one? It is called what you call a center of curvature. What is center of curvature? It is actually the center of the whole sphere of which the lens forms a part. Once again, what is center of curvature? It is the center of the whole sphere of which the lens forms a part. You can easily see here. You can see that one. I would like just show that one. Here you find that. This is center of curvature you are able to see. In the case of a convex lens, this is C and this is C. Here also you find that concave ugly, convex ugly, you find that. See that? I have marked now with C. That is, you find that it is the center of the whole sphere of which the lens forms a part. That is called what you call center of curvature. Since it has got two curved surfaces, it has got two centers of curvature. One on this side, one on other side. So, you have got two centers of curvature. How is it? They occur in pair because it has got two curved surfaces and therefore it is so. In the case of concave lens also, it has got two centers of curvature because it has got two curved surfaces. Okay, sir. And then I would like to take up what is radius of curvature. Before studying radius of curvature, I would like to just take up another one, that is optic center. And then I will just discuss something about the radius of curvature. I would like just mark here O. I call that one as optic center. You see that? Center of the lens. I put actually center of the lens. At the center of the lens, that is referred to as what you call optic center. What is the speciality of this optic center? Suppose a ray of light passes through which one? The optic center. It gets out of the lens undeviated. Very, very important characteristic you must understand. Once again, so optic center, it is the center of the lens. It may be concave, it may be convex. The center of the lens is called optic center. What is the speciality of this optic center? Suppose a ray of light passes through optic center, it gets out of the lens undeviated, whether it may be concave or convex. The ray that gets out of which one? In both the cases you find that if a ray passes out of or passes through the optic center, it gets out of the lens undeviated. ಇದನ್ನು ಚೆನ್ನಾಗಿ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಬೇಕು, ಮರಿಬಾರ್ದು. a ray passing out or passing through the optic center gets out of the lens undeviated. Because I have to discuss these things, sir, when I just take up the construction of images in the case of lenses. Okay, that is the next definition, that is optic center. It is the center of the lens through which a ray, if a ray passes out, what happens? It gets out of the lens undeviated. And then I have to just take up now the radius of curvature. Certainly the distance between the optic center, the distance between which one? The optic center, radius of curvature. Radius of curvature. See now here, please understand this particular point here. The radius of the whole sphere, the radius of the whole sphere of which, the radius of the whole sphere of which, the radius not OCL, it is the center, it is the radius of the whole sphere of which the lens forms a part. That is called which one? Radius of curvature. Radius of curvature is actually the radius of the whole sphere of which the lens forms a part. Over. Next one, I'll just take up the other definition of what we call principal axis. Principal axis means it is the line, please understand, it is a line passing through the centers of curvature and the optic center. See now, the line passing through, I will just, I will extend you one, I will extend here also. Now, here you see that. The two lines I have just written here. The straight line or the line that passes through the optic center and centers of curvature, that is referred to as what you call principal axis. Then I have just to think of the other definition, that is what you call which one? Principal focus. I think you know what is a principal focus. Suppose I just take a convex lens. First one, I just take a convex lens. I just pass a ray of light. I pass rays of light traveling parallel to the principal axis. You see that one? Please understand. I am just taking the rays of light traveling parallel to the principal axis. After refraction, they pass through a fixed point on the principal axis on the other side of the lens as I show here. You please see that. In the case of first one only. In the case of convex lens, the rays traveling parallel to the principal axis after refraction pass through a fixed point on the other side of the lens, that is referred to as what you call principal focus, that we call as actually principal focus. Adanna ನಾವು ಈ ಸೀದೆ ಅದನ್ನು ಚೇಂಜ್ ಮಾಡ್ತೀನಿ, ಇಲ್ಲಿ ಸಿ ಮೂಲಕ ಹೋಗಲ್ಲ. ಐ ಆಮ್ ಜಸ್ಟ್ ಸೇಯಿಂಗ್ ದಟ್ ಒನ್. ಸಪ್ರೇಟ್ ಫಿಗರ್ ಬರಿಬೇಕು, ನಾ ಬರೀಲಿಲ್ಲ. ನಾವು ಇದನ್ನು ಅಡ್ಜಸ್ಟ್ ಮಾಡಿದ್ದೀನಿ. ದಟ್ ಇಸ್ ನಾಟ್ ಸಿ ಆ್ಯಕ್ಚುಲಿ ಸೆಂಟ್ರ್ ಮೂಲಕ ಹೋಗ್ತಾ ಇಲ್ಲ. ಇಟ್ ಇಸ್ ಪಾಸ್ ಥ್ರೂ a fixed point in the principal axis, that is referred to as what you call which one? Principal focus. Suppose write the figure separately, you will be able to understand it much better. Okay, I would like to write the figure separately to just discuss something about the principle of focus of a particular lens here, because let it not be confused. Now I just should take a convex lens. I am writing a convex lens. Now I am just writing the principal axis and I am just marking out which one? The optic center. Now I am just considering two rays of light traveling parallel to the principal axis. After refraction, all of them pass through a fixed point, and that fixed point on the other side of the lens is principal focus. Please see that. I made it very clear now. Now I consider parallel rays traveling parallel to the principal axis. That is very important. After refraction, they pass through a fixed point on the other side of the lens, that is called principal focus of a convex lens. When I just take a concave lens, Now I write the figure now of a concave lens. Now I am just writing a concave lens. Okay, sir. Yes, I just write a concave lens. Okay, what happens? Suppose rays of light were to pass. Yes, sir. You'll be able to see that the rays, now I consider parallel rays traveling parallel to the principal axis of a concave lens. After refraction, they diverge away from a point within on the same side of the lens. They appear to diverge away from a point, F I call it. They appear to diverge away from a point within on the same side of the lens, and that is called principal focus. I repeat, I consider a pencil of parallel rays traveling parallel to the principal axis. After refraction, you find that they appear to diverge away from a point on the same side of the lens, and that is called what you call principal focus. And last one is the focal length. The distance between the optic center and the principal focus is small f, and that is f. Now you see that f. Principal focus is formed on the other side of the lens in the case of a convex lens, and for f is formed on the same side of the lens in the case of concave lens. F is considered to be positive or negative. Let us say afterwards sign convention. Here you just understand. Please understand F. F lies always on the other side of the lens in the case of a convex lens, and here F lies on the which one? On the same side of the lens, that is there. But because it has got two curvatures, F and C are present on both sides. C and F are present on both sides of the lens. That is there. But here, for our sake of reference here, to define principal focus, you find that principal focus is formed in front of the lens. F is formed there behind the lens, or you can say on the same side of the lens. Are you able to follow? And the distance between O and F is called focal length. That is there. Okay, and once again, you know that one, it is double the center of curvature, that is, center of curvature is double the radius of curvature. I think you know that one. I think in the case of mirror also, we just discussed, it is double that one. So, F is R by 2, or R is equal to 2F, where R is the radius of curvature and F is the focal length. R is equal to 2F, or F is equal to R by 2 over. They are actually the definitions. Now I would like to take up how exactly an image is formed in the case of a convex lens. In the case of a convex lens and in the case of so you please understand. So principal focus of a convex lens, concave lens ಎಲ್ಲ ಅರ್ಥ ಆಯಿತು, ಪ್ರಿನ್ಸಿಪಲ್ ಎಲ್ಲ ಅರ್ಥ ಆಗಿದೆ. ಈಗ ಇಮೇಜ್. I think I told you what is an image. It is actually, what is an image? It is a replica of the object form. I have already discussed all those things in the previous classes, and I have already given the differences between real image and virtual image. For sake of revision, simply I am just saying real image is always inverted, you must know that one, and real image can be caught on the screen and is formed by the convergent beam of light, and I have already told you all the differences. And in the case of virtual image is always erect and is formed by divergent beam of light. Divergent beam of light is formed by the divergent beam of light, and it is always erect. So virtual image is always erect. You know all these things because we have discussed all these things when we discussed the formation of image in the case of a mirror in the previous classes. Now I am taking into consideration the formation of image in the case of a convex lens. Once again, in the very first instance, I am just placing an object at infinity. The first figure refers to that one. If the object is at infinity, you must show that in the case of a convex lens, the rays coming out are parallel to each other and they'll be focused at a particular point on the other side of the lens, and that is where exactly the image is formed there. The image is formed at the principal focus of a convex lens. At F, the image is formed there. Once again, when the object is placed at infinity, the rays that are coming out will be parallel to each other, and you know what happens there in the case of parallel rays. After refraction, they will converge towards a point, and that is called principal focus. The image will be formed at the principal focus. That is the first position. Second position is when the object is placed beyond C. You please see that term. Beyond C. Beyond C. You know how to. Here also you have to consider once again a ray or two rays are taken into consideration. If AB is an extended object, I have just placed on the principal axis at right angles to the principal axis. I have considered two rays. What are the two rays that I have considered? One ray traveling parallel to the principal axis, another ray passing through the optic center. I have chosen only those two rays. Why is it that I have chosen those two rays only? Because I know what would happen to these rays after refraction. To trace that one, I have considered them. If a ray of light travels parallel to the principal axis, you know that it is bound to pass through principal focus. If a ray of light passes through optic center, it gets out of the lens undeviated. They are the two principles that I have just considered while constructing the image. Okay, sir. In the first one, you please see that. See that? The first ray, the traveling parallel principal axis, after refraction passing through which one? F, another one through O, it is there, it is intersecting. At the point of intersection of these two rays, the image of B is formed, which I have called as B dash. A dash, B dash is the image of the object. What are the characteristics? Now here, if you place an object beyond C, what are the characteristics of the image formed there? Yes, sir. What are the characteristics? Number one, it is a real image, and then therefore it is inverted image. And what is the size of the image? It is diminished, and it will be formed between F and C on the other side of the lens. It is formed on the other side of the lens. Once again, I am just saying what are the characteristics. It is a real image, it is an inverted image, it is a diminished image. It will be formed between F and C on the other side of the lens, as I have shown here in the figure. Now I'll just take up the object. Now it is placed. Where exactly I place the object? The object is placed. Yes. Now the object is placed at C. The object was placed beyond C. Now I am placing the object at C. I am just coming very near. Now here. The object is placed at C. Because I place the object at C, I can't put A. CB becomes the image. I consider two rays. One ray traveling parallel to the principal axis. After refraction is passing through F. Another ray of light passing through O gets out of the lens undeviated. At the intersection of these two rays, the image of B is formed, which I called B dash. Therefore, A dash B dash is the image of the object. From the figure, you are able to see that the image is once again a real image. Real image is always inverted, and if you just construct the image, you will be able to see that the size of the image will be equal to size of the object. Size of the image will be equal to size of the object. Same size, and where exactly the object is formed there? The image is formed there. The image is formed at C only. If you place the object at C, the image will also be formed at C. And the size will not vary, it will be of the same size. This is the second position. The third position. The fourth position I am just taking now. Between F and C. Suppose you place an object between F and C. Here I am just placing AB as the object between F and C. Once again I am considering two rays. One ray traveling parallel to the principal axis. After refraction is bound to pass through F, and another ray of light passing through O gets out of the lens undeviated. Both them intersect. Beyond C, you are able to see that one. From that one, I dropped a perpendicular A dash B dash. A dash B dash is the image of the object, and if you write the characteristics, it will be like that one. It is a real image, and therefore it is inverted. But you'll be able to see that it is an enlarged image from the figure. You'll be able to see that, and it will form on the other side of the lens. That is the thing there. By construction, you can see that one. I just take up the next one is at F. If you place an object at F, I can't write A there. FB becomes the object. FB becomes the object. FB becomes the object. Once again, I am considering two rays. One ray traveling parallel to the principal axis. It is bound to pass through F, as you see. Another ray of light starting from the same point B, passing through O, gets out of the lens undeviated. You will be able to see from the figure. They travel parallel to each other, and therefore you can't expect any image to be formed there. In the examination, they ask this question. If you place an object at the principal focus, no image is formed. Why? You will have to say that the two rays coming out of the lens, they travel parallel to each other, and therefore no image is formed. That is how you can see that one. I just go to the other position, that is between O and F, that is called within the focal length. Suppose I place an object between what? Between O and F. See that? You see that? The first figure here. Between O and F, that is within the focal length. AB is the object. Once again, I consider two rays traveling from or starting from B. One traveling parallel to the principal axis, bound to pass through F on the other side. And I am considering another ray of light passing through O. It gets out of the lens undeviated. But these rays, they form divergent beam of light from the figure. You will see that one. They will not meet. Suppose you produce it backwards, they are supposed to meet at a point B dash. And from B dash, if I drop a perpendicular, A dash B dash is the image of the object. Therefore, here you will be able to see that it is formed. This image is formed by the divergent beam of light, and therefore it should be what kind of image? Virtual image. Because it is virtual, it should be erect. And here from the figure, you will be able to see that it is an enlarged image formed on the same side of the lens. Formed on the same side of the lens. That's how you have to just construct the images in the case of a convex mirror. Now I will just go to the last part of it. Formation of images in the case of a concave lens, not mirror, in the case of a concave lens. Concave lens. Now here I just write the figure. I have placed an object wherever you may place the object at any place. Here I have placed beyond C here. And now AB is the object. Once again I have just considered two rays. One ray traveling parallel to the principal axis is bound to pass through F. You please see that? That is, it forms ಏನಾಗುತ್ತೆ divergent beam of light ಆಗುತ್ತೆ. ಅದು ಹಿಂದೆ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡಿದ್ರೆ F ಬರುತ್ತೆ. ಇನ್ನೊಂದು, it is passing through optic center. It gets out of the lens, undeviated. At the intersection of these two rays, a small image is formed there, A dash B dash. Once again, what kind of image is this? It is a virtual image, and therefore it is an erect image, and it is a diminished image is formed on the same side of the lens. So you must understand how exactly you should construct. So much so, we have finished what exactly the images that are formed when the object is placed at different distances with respect to convex mirror. In the case of a concave mirror, or not mirror, convex lens, we have discussed about lens, not mirror. So we have discussed enough. What happens? Akasmat mirror has a lens and the correction totally. During my lesson, if I just by mistake, if I talk like that, please take it as a lens. No mirror. It is a spherical mirror. Solaidu, a convex lens and convex lens and concave lens. Okay, you have just understood how exactly the image formed there. Tomorrow, I'll just take up the rest of the lesson. Thank you very much. Bye.